where everything is starting to ramp up and everybody starts now's the part where everybody starts to feel like you're slowly drowning in all the work you have to do, right? It's like, oh, the water's starting to come up again. So so let me add to that by saying that I have to give an exam in here next week, but I'm going to give you lots of, I had some concerned questions about this last time. Sometime I'm going to post information about it tomorrow, and then sometime this weekend, I'm going to post like a bunch of preparatory material that you should be expected to be able to work through. And because this is sort of a combination of a conceptual class, but with a lot of computational examples, in this class, you're basically going to see questions that look like the questions I'm going to ask you on the material, right? So we're going to cover the material that starts sort of the brief refresher in chapter 1 that we began with, which covered vector calculus. So if I'm going to, and then stuff in chapter 2, we're going to finish basically the part of chapter 2 that I want you to know for the exam, which is 2.6. We're going to finish that today. So anything that we talk about next week will not be on there, right? It's going to be everything up through the end of, I think it's 2.6 is the gradient and directional derivative chapter, and 2.7 is about Newton's method, which we're not talking about. Right? I might be off by one. Am I off by one? Is it 2.7 that we're talking about right now? I don't know why I'm asking you when I can pull the book open on my computer. We're talking. It's okay. So yeah. So basically, what the exam is going to cover is chapter 1 and 2.1 through 2.6. Right. So the stuff that we've talked about on the homework for like this this period right here. And you'll have a list of questions that are review questions. There'll be suggested homework stuff to look at. Your homework should be coming back. Your homework should be coming back on as soon as I can get the grader to give it back to me. Actually, so Monday is like, as soon as I get it back, you guys will have it back. So yeah, if you do not get your homework back, I will not give you the exam. That's the deal, right? So I can't do that. You have to have feedback before you take the exam. So if I cannot get it back, I will push it back to make sure that you guys have time to get some feedback on how you're doing on the homework. Okay, like I just make that deal. Okay. That's important enough to me. What's that?
I thought.
Yeah. Okay. So what was I talking about? Oh yeah. So last time we talked about ideas related to the gradient vector and level curves. And so we're just going to make that more formal today, because it turns out that the gradient vector is probably the most useful object that exists in the study of scalar valued functions. We're going to see it over and over again. The idea of the gradients can show up. And the reason is because a lot of the things that we want to study, how many of you guys have seen a scalar field before? You probably would have seen this. This is a scalar field. You should think about as being a continuous map that for every x and y input, it produces a z value to it. You think about it as attaching the value to that point. So a temperature map, for example, is an example of a scalar field, right? An altitude map is an example of a scalar field, right? To every x and y input, there's an output number attached to it. We call it a scalar field because it's scalars that are being attached, right? So I'm going to make a connection here. So part of the reason why we're going to focus here on the gradient today, and we're putting so much emphasis on the gradient, is that two of the main objects that we study in vector analysis are scalar fields and vector fields. And we're going to do both of them in here. And by a scalar field, you can think of function f. We'll just do it in two variables. We'll take some domain R2 into R, so a scalar value function. But now I'm going to think about this not as a surface sitting inside of R3. That is one way to interpret this. It's like you put an x and a y in and a z comes out. Instead, what you do is you think, okay, I've got this map x and y, and this is just a conceptual shift. It's not actually a difference in function. What we think of is every point has attached to it some number. And the x and the y value that you give, you can evaluate the function on that thing and you get some number attached to it. You may have seen these before in settings where these are called, I mean, anytime when you have scalar quantities that you're measuring, right? There's a lot of scalar quantities in the world. Temperature is one of them. So temperature is a standard one to be looking at. A temperature distribution in space, or across a plane, is really just, just you turn the weather on and look at the map of the regions of temperature in the country. What you're looking at is they are thinking of this, or the way they've generated that map is in the background somewhere. They came up with an f of x and y. They're plotting all those numbers on some grid that represents the United States or California or San Luis Obispo County, and then they're imposing level curves on it. So when you think about a weather map or a pressure map, what you're thinking about is there's a bunch of dots and some lattice. Each one has a numerical value attached to it. So on. And then normally, to make this easier to read, what we do is we chop it up like a topographic map of a mountain or a temperature map on a weather report, where we say these bands represent where the temperatures change from one temperature to the next one. So these aren't just abstract mathematical tools. This is one of the core sort of things that we study with this type of math, is these things that are called scalar fields. Now, at the same time, the way we've been talking about this so far is we've been thinking about these things as sort of being surfaces that sit in 3 dimensions. And this is another way of visualizing these things, right? Every x and y input gives you a height. Here we're thinking about this as being an x, a y, and a z. Why the gradient? Because the gradient tells us information when we think about these sorts of pictures. The gradient is an x and y vector. It's in the domain of the function. And so if we think about the function as being a scalar field, a set of points that have been blobbed down onto some Cartesian plane, and some level curves, some curves of constant temperature that have been attached to that, then the gradient always is going to, we're going to do this again today. I'm going to show you why this holds. The gradient basically tells us how things are flowing. If we thought about, so for example, if this was a mountain and I wanted to know how water flowed down the mountain, if I computed the gradient at every point along every level curve that I've computed, I'm going to get a flow lines that show me how water would flow through this surface, right? These are the directions of maximum change, and we can think about that as being, so one model is to think, well, if you put a drop of water right here, which direction would it flow? And at every level curve, it tells you which direction it flows, which means you get these flow channels across the map that you're working with. Another way that this shows up, and maybe something that's interesting to people who do who have any interest in thinking about data science or optimization problems, is there's this fancy method in data science that's called gradient descent. And for gradient descent, what you do is you get a whole bunch of data plotted out on some grid, right? You think about, I've got this lattice of data, and I construct these contour lines numerically. Where are the values that I've put out on this grid equal? The z coordinates equal. And then if I want to find a local maximum, what I do is I say, okay, compute the gradient right here. What does the gradient say? Well, the maximum direction is this direction. The minimum direction must be the other way. Maximum is a maximum change up is in one direction. It's going to turn out maximum change down is in the other direction, parallel to it in the other direction. So if I want to find a minimum, I can compute the gradient and just go backwards until I hit the next surface and say, okay, now what direction should I go? Compute the gradient and go backwards. Compute the gradient and go backwards. And the idea is the gradient will crawl down the mountain or up the mountain to find a local max or a local min. Gradients are incredibly useful for modeling. Again, maybe I have to emphasize more without sort of like ridiculous picture. I'll draw another ridiculous picture. If you didn't know where the local minimum, so imagine this function kind of comes up from this bowl and you're looking for a minimum, which is typical in optimization or data science problems. You're trying to recover things like this. The method for recovering the x and y values of the max or min of the function you're looking for is pick a point, compute the gradient. Now you don't even really need to figure out where these contour lines are, right? You don't need to do that. You can compute numerically what the gradient is. But when you do it, you're automatically moving like in a direction that's perpendicular to whatever the constants are. So you don't even need to know the lines. You just need to know the gradient, and it still tells you which direction to go. So you compute a gradient and it puts you here. Compute a gradient, I'll go that way. Compute a gradient, go this way. Compute a gradient, go that way. And eventually, if you do this process enough, this thing will settle down to little tiny motions. And you don't leave these little basins. And then you're done. You found it. You found a place where the gradient can't escape from, which means there's no way to leave. You're in there, you can't leave. The gradient descent, if you've never seen it before, is pretty awesome. It's based on the core ideas of vector calculus. All right. So I'm trying to, you should take it as a given that I recognize that there are big pieces of this class that are probably dry as a desert. I'm doing my best to try to hook it up with like why we're doing this. I know this is overly technical at times, or seems overly technical, and it's not always clear why I'm setting up what I'm setting up. But the ideas that we're building out in here and the notation we're building out are in wide use all over the mathematics. If I could make it more interesting on a minute-to-minute basis, you guaranteed I would be finding places where I can. Okay, so let's talk about specifics here today. Okay, so remember again that the gradient is defined to be df was the x1 derivative up to the xn derivative for a function f. We took a domain in Rn into R. It is only defined for these scalar fields. Here's a theorem I hinted at yesterday at the very end, but did not prove. And I'm actually not going to prove it today, but at least I'm going to state it. So here's a theorem. Let X contained in Rn be open. Why are we constantly writing this condition about openness? Because I'm trying to pound it into your head. The differentiability only works on open intervals or open domains, right? Stay away from boundaries with these methods. Let X in Rn be an open set. And let's let f taking X into Rn into R, let's let that be a differentiable function. Differentiable. Then we get the remarkable result that d, v, f, and a, what does that mean? Somebody give me the whole blog. Directional derivative of in the direction at the point. Beautiful. The directional derivative of f in the direction b at the point A is equal to the gradient. I should say that this thing exists in all directions and I get it by taking the gradient and dotting it with the direction vector.
So V is the direction.
Yeah, so V here, yeah, so V is a direction vector. This V is the same as this V, and they're unit vectors. Yes, that means V is a unit vector. You don't actually need to use unit vectors, but if you don't, things get ambiguous. So we just say only, why would I include more than one vector in the same direction? Let's just work with unit vectors. Okay, so this is pretty nice because it means that directional derivatives are incredibly easy to compute. So there's another feature here that maybe is not immediately obvious. If I say the directional derivative exists in all directions, that means no matter which direction I point, there's a tangent line, which means there's no folds and there's no kinks and there's no cusps of a function like this, right? As I spin through all the different directions, I have a tangent line in any possible direction I choose to go from A. So there's no defective behavior going on in the surface of this line. So we really want to avoid those. So differentiability of F gives you directional differentiability. And we get this beautiful computational formula. Now, I'm curious if anybody could think about like, if anybody has a guess for what is the maximum value that can come out of the directional derivative? What direction do I have to point? This guy better be in the same direction as the gradient, right? Like as I rotate through all possible directions, as soon as I'm pointing in the direction that the gradient points, I've maximized. It's going to turn out to be the case I maximize my slope. The steepest tangent line happens in the direction where I'm pointing the same direction as f. Does anybody know why that's true?
The gradient is grade stream.
But why? See, I said it, but I didn't say why it was true. Why is it true? Somebody actually raised this last time, and I remember who it was that was asking about the cosine version of the dot product. Who was that? Does anybody remember another definition of dot product? The dot product of two vectors? It's okay. Yeah, okay. So u dot v is equal to the length of u, the length of v times the cosine of the angle between them, right? I mean, that's a way of defining what that's where the dot product comes from, right? The dot product, when you first define it, you set it up by talking about a right triangle situation, and the law of cosines is involved, okay? So this is another way of defining the inner product, or the inner product of dot product. So when is this going to be the largest possible value? When theta, I mean, if b is a unit vector, that's always going to be 1. So you maximize this when theta is equal to 0. You minimize it when theta is equal to pi, because pi spits out a -1. Cosine varies between 1 and -1. So why is the gradient point in the direction of greatest increase? Because the gradient of f in the direction A dotted with the vector b is also equal to the length of the gradient vector, well, times the length of the v vector times the cosine of the angle between them. But that's always 1. We've chosen this to be a unit vector. I should do that. That is bad pedagogical practice. The gradient of f A times the cosine of theta. And notice there is no dependence here on the v, the length of v at all. So if I want to maximize what's happening over here, I set theta equal to 0, which makes cosine equal to 1. And if I want to minimize what's happening over here, I want this to be -1, smallest value that can come out, which makes this into a -1. And in both cases, the length of the gradient vector tells us what the slope is. So delta v, nabla v, or whatever reason. Nabla f at A dotted with v is maximized when v is parallel. Oh, let's not say that. In the same direction as the gradient of f at A, which is basically saying theta is equal to 0. And then in that particular case, the directional derivative is equal to the gradient vector. If I want the smallest possible value, which means the most negative slopes, the direction of greatest descent as opposed to greatest ascent, I just let theta equal pi. So if theta is equal to 0, or theta is equal to pi, then cosine of theta is equal to 1, or cosine of theta is equal to -1. That's the basic idea of this. Does that make sense? Okay. So this is basically the argument that proves that the direction of greatest change. There's a big geometric idea here, which says that the directional derivative, I'll say it in words, the directional derivative maximized in the direction gradient of f at A, it has magnitude absolute value of the gradient of f at A, so the length of the gradient vector, and it's minimized in the opposite direction. In which case the magnitude is the negative of that.
Or was that the magnitude of?
The magnitude of, it's this magnitude, the length of the gradient vector evaluated at A.
Oh, that's it.
Is that clearer?
Yes.
Okay. Yeah, no, like I said, I get excited sometimes when I write fast. I mean, I really like the idea. It's like the idea, it was pointed out to me that like the process of continually learning analysis is throwing more and more of the analysis away and putting more and more geometry into it. And this is essentially a geometric result, which is, I don't have to minimize or maximize anything. I always know what direction to go if I want to maximize my change. Just calculate it.
I don't know if this matters much in this class, but these are all local minimizers.
They are local. All of this is all local. Yeah. So when we talk about this, we mean, so the directional derivative is, we're anchored at this point A. So it's local in the sense that this is a local, this is actually absolutely like important point here. Each point A, each point A has a potentially different, has its own df. Is it possible that the gradient of f could be ill-defined? Can you imagine a scenario where the gradient of f wouldn't make any sense? So what I'm saying here is, as you move around in the domain, every domain point you stick in is going to produce a different gradient potentially, right? Where is it possible that the act of taking a gradient could go wrong? Like, is it possible that I could have a nice function on which the gradient doesn't make any sense? Interpreted in this way? Because I mean, you know, the thing we're laying out here is you've got these contour lines and everything is perpendicular on the contour lines, but like there's real surfaces going on in the background, and the gradient always tells you the direction of greatest change. When could that go wrong? Yeah, if you're flat, you're going to have real trouble, right? Like if you're a flat plane and you computed a gradient, let's just suppose that your function was f of x and y is equal to 1. That seems like a perfectly reasonable function to define, right? Just the plane that no matter where you are at in x and y, you're always spitting out height 0, right? You just float along at height 0 forever in every possible direction. What is the gradient of f? Well, not f of 0, 0, f of x and y, no matter where you compute it, gradient of f is equal to fx, which is 0, and fy, which is also 0, right? The derivative of this function with respect to the x variable and y. You don't see the x and y values there, but they're there, right? Okay, well, if you get gradient f is equal to 0 out, you got some issues. Because either it means you can't go any lower, as in the sense of you have this kind of scenario. You took the gradient at a vertex of some sort of paraboloid right here, you're going to be at a point where the gradient is 0 vector. So 0 gradient could correspond to places where you have these 0 vertices. However, unfortunately, the gradient vector would also be 0. What I want you to imagine here is that this flattens out so that the tangent line is a flat plane, right? That's the idea. If it looks flat locally at a point, then the gradient's not going to know what direction to go because every direction looks like you're staying flat. There's no direction you can go. This. There's f of x, y equal to 1. You're going to have issues there too. Gradient doesn't make any sense. Of course, that's not a very interesting function. You've got to be careful with, like, it's possible the places where the gradient spits out 0 values are going to turn out to be really important when we're looking at sort of like the problems we're talking about later. In the same way that derivatives told us where the critical points of functions are, like derivatives of functions tell us where the function looks locally constant, the gradient is going to indicate the same sorts of ideas to us. But the problem is in 2 variables, you have lots of different ways that can happen. You don't just have constant lines, you can have planes, things that look flat like this at the bottoms of parabolas, say, where they have 0 slope, or places, right, here's your, have I drawn one of these for you guys yet? I must have. All right, I'm gonna see if I can do it.
Oh, yeah.
Because the parabola comes out this way on this side. There. That's right. I think I told you guys that there was a drawing challenge in here if you could draw one of these things. Okay, so the problem here is that this point right here will also tend to produce a gradient that doesn't know what direction to go. You can think about this as this can be flat in the sense that locally this looks like it has critical point in both the x direction and the y direction, because it's a parabola in this direction coming together with a parabola that's sort of rotated and coming together. So it's flat. It has a flat tangent plane there. The problem is in one direction it goes up, in the other direction it goes down. And so we're going to have to distinguish using the gradient, or be careful with the gradient, because the gradient won't be able to tell us the difference between these cases. So the gradient is awesome, and it acts in a lot of ways like the actual derivative does in one variable for detecting these points, except we have this ridiculous stuff that we've got to keep track of, and that's just in two variables. So there'll be more machinery we need to introduce when we actually start working on optimization. Yep.
If the gradient zero, we consider it a local minimum.
It doesn't have to be a local minimizer. Like this is neither a minimum nor a maximum. If you took 248 and remember it, you would have learned about this as a saddle point, is what this is called. Saddle points are points where we don't have a local max or a local min, but the function is still locally flat. Right? And that can't happen in one variable. There is no such thing in one variable. Either you're always at a local max or a local min. Actually, no, that's not quite true, because you could have these dudes. Right? Here the function gets flat, but it's not a local max or local min. It's the same thing. Okay. Actually, that I wanted to ask you guys, do you know what we talked about smooth functions. Have you ever seen like functions in this family? Because I want to imagine like how you say, oh, well, a plane, how could that ever happen? You know, a plane. I mean, it's to be obvious, it's a plane, it's got a flat piece, it's flat forever, it's a plane. Problem is that there's functions that are not planes that have flat pieces in them. So I was curious if any of you guys in your mathematical studies or engineering or science studies had come across the idea of taking two flat pieces and connecting them with a smooth function. This is an idea that you've seen before. So this comes up in modeling a lot, right? So if you had, say, I just want you to be aware this exists because there's going to be analogs over here when we start doing the derivatives. Imagine you got a function that goes along like this for a while. And a mathematician comes to you, with me, I show up and I say, it's a step function. It's equal to nothing right here. And then, then it just immediately leaps up. But you're an engineer, a scientist. You say, there is no such thing as a discrete change of state in nature, right? This is impossible. You can't do this. You can't go from something to nothing to something, right? There's got to be something to ramp up. And if I want to model this, it's not good enough. I can't do that. I can't just say like, oh, it's on, jump discontinuities. That's not the way a physical system reacts. So the idea is that like when you have these sort of things, I know I'm kind of throwing a grab bag of like side examples at you now, but these are the sort of objects that we have to wrestle with when we start doing these kinds of derivative investigations. The way that these things really act is that there's some little tiny window where there's nothing happening. You think of it as nothing happening. It was here and it is here, and something happens in between. And the way that these things are modeled, and we talked about smooth functions last time, right? C infinity functions, functions that have infinite derivatives. I can make a perfectly smooth little function in here where I join it at the corners. This thing at these conditions right here where it joins up matches perfectly to every possible derivative. So this is a smooth function. It's smooth because it has infinite derivatives everywhere. If you're over here, the derivative is equal to 0. If you're at that point, the derivative is equal to 0 at any possible derivative you take, because I've built this function so that it matches smoothly with the constant function, and on the other side as well. But these turn out to be incredibly useful to work with, and also terribly designed for optimizing with, because you can't see the corner, but you can't approximate the function either. It's constant on one side and not constant on the other, and that's an ugly function. Okay. So be careful. Like why am I giving you these examples? Because I'm trying to indicate on the one hand, I'm telling you the gradient is awesome and we can do all these cool stuff, cool things with it. But on the other hand, there's going to be things like this that look nice, that are very natural to consider, but that are really difficult to look at. Okay? So gradients are, any constant function could be like discrete constant functions can be turned into perfectly continuous, perfectly differentiable, infinitely differentiable functions. Be careful with the gradient. Or you could treat it like an applied mathematician. I guess Dave's not around. So you can treat it like an applied mathematician does, and you just do it. And if you get the right answer out the other side, then you were justified in doing it. That's the applied mathematician's strategy is, I didn't know if this was valid, but I did it anyway. And I got an answer out that looks like reality. So it must have been okay. Okay. I guess the last thing I want to point out is the gradient gets us a really, really fast way of producing tangent planes if we're working in R3. This is one of the most useful things that it does. So it turns out to be the case that there's a lot of functions. There's a lot of surfaces that you can define in R3 that aren't even functions. It's like, what is this? Radius. Is it a function of x and y? Well, some places it is, and some places it isn't, because it gets vertical. One, it's doubly defined everywhere, and then there's places where it's vertical, right? Vertical functions don't act very well when we're working in 2 dimensions, right? So I'd really like to be able to write down tangent planes for this thing, but it's not a function, and all definitions of tangent planes so far have involved functions. You inhaled as if you were to say something. What were you going to say? Okay, so here is the way that you have learned in earlier classes to deal with this. Z squared is equal to the Z is equal to plus or minus the square root of 4 minus x squared minus y squared. Figure out which half of the sphere you're on, and then use the partial derivatives to write down the equation of the tangent plane using h of x and y is equal to f of AB plus fx at AB times x minus a plus fy at AB times y minus b, but make sure you don't slide off the edge of the hemisphere because your approximation is going to fall apart. And also I've got like derivatives of square roots just make my soul hurt. And I mean, double branched functions, I don't want to have to think, I just want to do, right? I don't want to think about a problem. I want a method for producing these. So yes, you can rewrite the function, get 2 branches, compute the partial derivatives, and come up with 2 families of tangent planes that describe what's going on in the function. Each of these will describe a local flat approximation for one piece of this function, but not both pieces. If only there was a way to do it where I didn't have to do the thing where I solved. So it turns out that in R3, this actually works in higher dimensions as well, but in R3 it's the easiest to justify. In R3, that the easiest way to write the equation of the tangent plane is my theorem. That's the perpendicularity theorem. Here we go. If S is a surface, defined by f of x and y and z is equal to some constant c, then the gradient of f at any point x naught dotted with the vector x minus x naught is equal to 0 is the tangent plane. This is the local approximation. The tangent plane to S. Why? I'm actually curious if anyone sees why that theorem must be true. Why must it be the case that if I compute the grade, I've started with this very specific setup here. I got some function equal to a c. So this you can think about as being a level curve, but a level curve sitting in 3-dimensional space instead of in 2-dimensional space. It's a level curve, right? This function is constantly equal to some value. But we know the gradient for a level curve is always perpendicular to that curve, right? So if this is a surface of constant value in the 4th dimension, then the gradient vector must be orthogonal to it. So we're sort of we're cheesily thinking of this as a surface in R4 to produce a tangent plane using 4-dimensional geometry, but then pretending we're not in 4 dimensions. Right? This is one of these, like, I don't know if you can see what I mean here, but in the same way that in 2 variables, we think of the contour lines as being curves inside of an XY plane, and we say, oh, the gradient is perpendicular to the contour lines. This is a constant level set of a 3-variable function. And it still turns out to be the case that the gradient is perpendicular to it. So the gradient of a function x naught for any point living inside this surface will be perpendicular to the surface, which means I can use it to generate a tangent plane to the surface. This is a wonderful theorem geometrically. And what it means, you might think like, okay, well, so what? So you can do stuff like this. You can say, in the case where, I mean, basically, let me draw a picture of what I'm saying here first. The picture says, if I think about this as a level surface, it has the same setup as a level curve in 2 dimensions. It's a level surface. It's because the constant, the value coming out of the f of x, y, and z is always the same. So if you pick a point on the surface, that's the x naught, and you compute the gradient vector, it's going to poke out like this, so that it's perpendicular to the surface that you've computed it at. Well, once you've got a perpendicular vector in a point, you've got a plane. That's what a plane is, right? A perpendicular vector dotted with everything orthogonal to it is equal to make sure everything dotted with it is equal to 0. So the plane that's attached to that vector can be gotten by taking the normal vector f of x naught and dotting it with any direction that starts at x naught. And that's what this term is. The normal vector is the gradient. The direction vector from our anchor point is x minus x naught. This is an absolutely elegant way of writing down tangent planes. So that means if I want a tangent plane for this function, I can just do this. Gradient of f is equal to 2x, 2y, 2z. The gradient of f at x naught is equal to 2x naught, 2y naught, 2z naught. X minus x naught I can think of as being the vector x minus x naught, y minus y naught, z minus z naught. And if I want the tangent plane, I just dot those. 2x naught, x minus x naught, plus 2y naught, y minus y naught, plus 2z naught, z minus z naught is equal to 0. This is used all the time. The reason we use this all the time is because I don't have to worry about unsorting a function that's not, I mean, this works on implicitly defined functions, I guess is the idea. So that's not a function of x and y, but I can still very easily compute this tangent. And this will also capture those edge cases where you're going around the diameter of the sphere in your vertical. This will represent those as well. The nice thing about this technique is it actually works even in the case where you have an f of x and y. So what do I mean by that? Let's suppose somebody said, I want to find a tangent plane to a function that looks like this. Just z is equal to f of x and y. Well, notice, anytime I write down z is equal to f of x and y, I could just have easily have written 0 times f of x and y minus z. That's the same setup. This is a function of x, y, and z is equal to some constant. So the same game actually applies to regular old functions and 2 variables in and 1 variable out. As an example, if I said compute a tangent plane to z is equal to the natural log of x, y at the points x, comma, y, is equal to 2, 2. I could grind out a bunch of partial derivatives. Or I can compute directly by saying this. Well, if if z is equal to the natural log of x and y, then the natural log of x and y minus z is equal to 0. And the tangent plane formula says I can find a tangent plane for this object by writing down the gradient of f evaluated at the point 2, 2, and then whatever the z value that goes with 2, 2. But what is the gradient? What's the z value at 2, 2? Log 4, right? Z that goes with this, the z naught value is just the natural log of 2 times 2, which is the natural log of 4. That's the only piece of work we have got to do is figure out the function value, which we would have needed anyway. The gradient of f evaluated at 2, 2, and the natural log of 4 is equal to 1 over, so it's y over xy, x over xy minus 1. Partial with respect to x of this thing, partial with respect to y of this thing, partial with respect to z of this thing. That will always be a -1 here if this is just a function of a z. Evaluated when x is equal to 2 and y is equal to 2. Well, that just means that this is 1/2 minus 1. What's the tangent plane? 1/2, 1/2, 1 dotted with x minus 1/2, y minus 1/2, e minus the natural log of 4. That's a pretty nice way of doing things, I think. You have access to sort of set up with the gradient, right? This is, I think anyway, if you're used to the way that the gradient works and using the gradient to define these formulas, even though we're sort of piling up the notation from a computational standpoint, there's something thematic about the fact that the gradient keeps showing up, right? The gradient is the vector, this quantity that studies these functions. Yeah, did I do something wrong? Yeah. It's the original point. X minus 2, y minus 2, z minus log 4. Yeah. It's the x naught, y naught, and z naught. Give you the point where you approximate. Okay, so the idea of the gradient, and so like what's the big theme of what we're doing here? So the sort of, we're done with chapter 2 now, with the content I'm interested in from chapter 2. And the big theme, there's 2 big themes I want you to take away, which is the first theme is that derivatives are most easily thought of as matrices, right? Vector valued functions tend to have derivatives defined in terms of matrices. Vector valued functions have matrix derivatives. First thing, encode all the information. 2, scalar valued functions mostly when we think about scalar valued functions, we think about them as having gradient derivatives. And what do I mean by gradient derivatives? The gradient told us every directional derivative. It tells us the partial derivatives. It tells us the tangent planes. The gradient tells us everything for scalar valued functions, right? So for scalar valued functions, the gradient is the key tool of what we use. For vector valued functions, we did everything in terms of matrix derivatives. And the third big theme is that the point of it all is linear approximation. So theme 3 is we want to approximate. And we're approximating right now with lines. The last thing I'll leave you with, I think before we close this up for the day, I'll finish a little bit early today. The last thing that I want you to take away from this is, where could this go? Right? Where does a theory go from here? So there's two things that are going to happen. The next thrust of the class is going to be to use the ideas that we developed here to study the way objects travel in space. So we're going to use these ideas to study motion through space and vector value, like sort of parametric curves, basically. So we're going to study things like curvature. We're going to study things like scalar fields. We're going to study vector fields, so like physically motivated functions. They're not always going to come from physics, but the ideas are physically motivated. The second idea is, why should I have to approximate just with lines? Right? Functions are much easier to approximate if you allow them to be parabolas as well, right? And approximating parabola is more accurate than approximating line. Approximating cubic is even more accurate than that. So the first big move will be to study physically motivated functions. And the second is going to be, we're going to look at nonlinear approximation. And as somebody in here guessed, that's going to mean Taylor polynomials. So Taylor series turn out to be a really, really, really useful idea in more than one variable as well, but also kind of a total pain to deal with. Because as you can imagine, if the Taylor series, if you remember the past, Taylor series were built out of the derivatives of a function, right? That's the whole point of a Taylor series, is you build it from derivatives. But a function with lots of variables has a lot of derivatives. So we're going to have to come up with some way of developing and writing down the Taylor polynomials that collect that together in a useful way. So these are the two ways we're going from here. Chapter 3 is going to be to study physically motivated stuff. In chapter 4, we're going to look at, also in chapter 3, maybe at the end of chapter 3, is going to be looking at Taylor polynomials and nonlinear approximation. All right. So yeah, I'm going to post stuff about your what you should be getting prepared for. If you don't see it tomorrow, then check for it over the weekend, and then you can ask me direct questions about it next week. Good.
I've got a question
Sure.
about